In standard spectral geometry, Current's nodal domain theorem establishes a reliable baseline. It tells us that the Laplacian ground state on a smooth, orientable manifold will always be strictly positive and completely nodeless. But on a Möbius band, the orientation line bundle forces a different reality. Because traversing the core loop flips the manifold's orientation, any valid wave function, a section of this bundle, must reverse its sign upon completing a circuit. This mandatory sign reversal, a property known as non-trivial holonomy, means a globally positive, smooth ground state is mathematically impossible. The function has to cross zero. We compound this topological twist by giving the surface a constant curvature metric, defined by the coefficient f of y equals cosine of y over r. At y equals pi r over 2, this metric vanishes, collapsing an entire transverse fiber into a single sharp cone point at the pole. The topology outlaws a positive ground state. However, this geometric collapse introduces a limit circle singularity that acts as an analytical escape hatch. Instead of forcing the spectrum to stay strictly positive, the cone allows the bottom eigenvalue to fall to zero or even drop into the negative. This energy level diagram illustrates the behavior of the ground state. It reveals a paradox. The final value of this lowest energy state is not dictated by the geometry of the Möbius band, but is determined by the choice of self-adjoint extension. Under the Friedrichs extension, the standard choice for conic singularities, the ground state locks in at exactly zero. But if we apply a Pascain-Prandy bridging extension, we enforce a boundary condition across the cone using a renormalization length. The result is a single cone-localized bound state with a negative eigenvalue. Yet, while the ground state fluctuates based on the mathematical framing, the first positive eigenvalue remains stable. It forms a rigid curve that yields a sharp kink at a specific bandwidth, immune to finite energy extension choices. The central analytical question is why the singularity shifts the ground state, while the first positive state remains unchanged. This diagram maps the constant curvature Möbius band onto a flat, two-dimensional rectangular domain. We apply an orientation-preserving isometric involution, mapping coordinates across seams to recreate the non-orientable topology. The collapsed cone point sits exactly at y equals pi r over 2, pinching the width to a single point and forming a figure-8 boundary. Because the metric coefficient depends solely on the longitudinal axis, y, the overall twisted Laplacian operator commutes with the transverse Neumann Laplacian. This allows us to separate the variables into two distinct sets, an even transverse family, which includes the constant k equals 0 mode, and an odd transverse family. By breaking the surface down into these separate transverse sectors, we isolate the topological twist and the cone singularity into independent, one-dimensional Sturm-Liouville problems. The operator loses its essential self-adjointness in exactly one specific place, the k equals 0 constant sector. Near the cone point, the weight function of the metric vanishes linearly, behaving asymptotically as delta over r. When we balance the leading order terms of our reduced equation against this weight, we derive a specific indicial equation, s squared equals 0. This plot maps the two local solutions from that double root. A regular branch flattens near the origin, while a logarithmic branch dives into a deep asymptote.
Crucially, integrating both against the linearly vanishing weight yields a strictly finite area. Because both the regular and singular branches survive, the cone acts as a limit circle endpoint. The mathematics does not naturally filter out one of the solutions, requiring a human choice for the boundary condition. To restore self-adjointness, we evaluate the cone boundary form and select a two-dimensional Lagrangian plane, a set of boundary data that forces the fluxes and values to cancel out. The Friedrichs extension makes a precise choice. It forces the flux data, specifically the logarithmic coefficient, to be 0 on both sides of the cone. Suppressing that logarithmic divergence generates a zero mode, phi 0. We see it as a discontinuous, piecewise constant state, a flat positive value on one half and a flat negative value on the other, passing through the singularity with no slope. The bridging extension instead enforces a Kirchhoff flux matching condition across both halves. This deforms the antisymmetric spectrum. The piecewise constant lines warp and plunge downward at the center, forming a deep logarithmic spike at the cone point and yielding a negative eigenvalue. The ground state is not a physical absolute of the surface. It is a mathematical projection, reflecting the specific boundary condition imposed on the limit circle. If we shift focus to the non-constant transverse sectors, the even modes where k is 1 or greater, and all odd modes, the Nath behaves differently. In these sectors, the indicial exponent, alpha, is strictly greater than 0. For exceptionally wide bands, the first odd sector might technically enter the limit circle regime. However, its singular branch requires infinite Dirichlet form energy. Any finite energy semi-bounded extension automatically rejects an infinite energy state. By default, the operator is forced to select the regular branch. Because the singular branch is mathematically outlawed here, the extension ambiguity vanishes. The non-constant sectors remain pure expressions of the intrinsic geometry. This chart plots eigenvalues against bandwidth, framing the ways for the first positive state. The constant sector provides a symmetric zonal mode. Independent of width, it remains stable at 2r squared. The odd sector, governed by a symmetric Peschel-Teller potential, contributes an eigenvalue scaling inversely with width. As the band widens, this descending curve perfectly intersects the flat line at a critical width equal to pi r over 2. This intersection marks the specific width where the manifold's lowest energy cost switches from the longitudinal to the transverse direction. In the narrow regime, before that critical width, the dominant eigenfunction is positive in the interior and smoothly vanishes at the identified seams. In the wide regime, the odd mode takes over. It forces the eigenfunction to change sign across the loop, splitting the surface. This structural shift is a direct result of the orientation line bundle. The non-trivial holonomy forbids a globally positive solution, forcing the geometry to calculate exactly where to place its mandatory zero crossing. The geometric collapse of the cone point offers an escape for the absolute ground state, but leaves its final value dependent on the mathematical convention. Final conclusion. While the ground state of a singular Möbius band depends on the choice of extension, the first positive state, and its width-dependent nodal shift, survives the singularity as a geometric invariant.